Hi all. In this video, we are going to present a paper, a very famous paper, YOLO. You only look once for real-time object detections. So the motivation comes from the key inference that human can glance at an image and very instantly can able to obtain a knowledge on an image. More specifically, what are the different objects and different classes of object present in an image, how those objects interact with each other to represent the scene of the image. So in order to get this kind of instant image observations, we need fast accurate algorithms for object detections. For applications, this can be applied for autonomous driving. But currently we have like a two broad based approach. One is a sliding windows approach, where it generates many bounding boxes sliding along the different patches of the image, which is computationally very expensive. It is called an exhaustive search. And the second one is called as selective search, which is what utilized in the RCNN. But still, if we are even though RCNN is a bit advantage, giving only a potential bounding boxes, very less number of bounding boxes compared to the exhaustive search. But in coming to the real time, it's very slow and also it's very hard to optimize. So to address these limitations with the existing systems, and this paper suggests a single regression problem. It formulates object detection as a single regression problem, whereas where it straight away computes different bounding boxes, its coordinates and its classes from straight away from the image pixels, which is different from the faster RCNN. So that is the name. It says you only look at once at an image to predict the bounding boxes and its class probabilities. So again, to emphasize, in a figure one, it glances at an entire image and it is put up on a single convolutional neural network in order to get different bounding boxes and their class probabilities. So the contributions for this paper, YOLO, is 3.1. It is a very extremely fast because it straight away bypasses certain computational things uh, for example, if you are going into faster RCNN, it tries to put a pre-processing layer, like it puts the deep convolutional neural network layer in order to extract this feature maps. This feature map is then put up into a regional proportional networks and the classification layer in order to get a different region of interest and their classifications. But here it's a straight simple enough. It straight away looks into the image and try to have a try to extract those information straight away from the image, completely avoiding the pre-processing steps. So it's extremely fast due to that reasons. The second is it has a global information about the image, because it looks at the image at only once and extract all those bounding boxes informations only looking at only one time at the image. So compared to RCNN, which I mentioned about earlier, it has a pre-processing layer. It doesn't have can't see about capture the larger context. And third one is, as it claims that it has a generalizable representation. It means that it can generalize even for like an images, training image, even for images during the test time, which doesn't put into a distribution of the training image, which has it means that in this image context or in the object detection context, it can able to identify unknown aspect ratios, which is not embedded in the training data. But however, it has a very drawback limitation compared to the two-stage process. Still, the accuracy is not that far compared to the two-stage process, like selective search procedure along with the RCNN. So that's what this paper claims about. So if you are looking into the deep contribution of this paper, which is explained in the section 1, it says that it's a unified framework which has a single neural network looking into an entire image as an input and try to predict the different bounding boxes. And for each bounding boxes, it tries to predict what are the classes belongs to that particular bounding box. It's a combined version of faster RCNN and multibox. So similar to fast RCM, it divides the input image into certain S cross. In fast RCM, we mentioned that it divides into M cross N grid. It divides into S cross S grid. Each cell belongs to a particular object and particular category, and from each cell or each grid, it generates multiple bounding boxes and tries to obtain confidential scores for each bounding box. Only the higher confidential scores are encouraged to go further into a training stage. So each bounding box is represented by a centroid location and the width and the height. And these are the class probabilities, and this is what the information is related to that. And the wrong information is either penalized by the wrong if that grid cell is not belong to any classes, or it can also penalize but if the bounding boxes is not related to the true scale and aspect ratio of the ground truth uh, bounding box. So that's what this says about. So this grid will be giving into a bounding box plus confidence and also the class probability, and then the final detections will be coming. So it has two layers. One is for regression and another for the classifications. So network design is a single convolutional neural networks, and finally in the network layer will be have a regression layer and a classification layer. So this is what network structures. It has 24 convolutional layers followed by 2 convolutional layers. Then it will be the image is not high resolution as like in ImageNet classifications. It has a scale of order 1 less than the what is utilized for ImageNet. But during the training, first it is these the convolutional layers are pre-trained for classifications for ImageNet. Then the final layers are removed, and then the layers are converted to convert that into an object detection, so putting a regression layer and the classification layer. As mentioned earlier, it doesn't go for 448 full resolution, it can only for half a resolutions. Then then it optimizes specialized training objective functions, which goes for regression things. This is for the classification things. This is for assignment problem similar to the multi-objective multi-box things. A multi-box paper, if you are looking into that, it will have this called an assignment problem. Either it can be 1 or 0. So this will give this optimizing this will straight away will give us bounding box for each grid cell and their confidential score and also the class probabilities. But there is a limitation with respect to this one. This is called as sum squared loss. And the first limitation is there are many negative samples compared to the positive samples. In order to mutually balance that, this lambda for no objective is being reduced, and for the other things it's a bit higher, like 5. The second one is the scale issues. For higher image, that regression error, small offset in the regression error is not that much to be attended, but for a small bounding box or even for a small deviation, that has to be attended. So this been addressed through a different way of setting to optimize square root of the width and square root of the height. And the third limitation it lies is related to large and small box. Sorry, the third limitation it lies with respect to giving multiple bounding boxes per grid cell, because each grid cell can only classify as a single object. At most it encourages to go for a high confidential, go for 2 bounding box, not more than that. So this is a kind of a limitation with respect to this objective functions. So this, as mentioned, this one is penalizing the classification error. This one is penalizing bounding box errors, and this has been trained by a stochastic gradient descent with momentum and decay rate and batch size. And for this is the training set with 135 epoch. And these are the for initially it has high decay, then it can decrease again. It is increased, and then again it is decreased. So over usual the standardized things, therefore avoid overfitting, they use dropout and data augmentations. And during the test time, it is really fast, because it just predicts only around 100 bounding boxes per image, and assigns a class probability for each box compared to the 2000 bounding box per image with the RCNN and fast RCNN. These are the this is real-time object detections. It's claimed and it has done reasonably upgraded version of multi-box and faster RCN, but still it has a limitation as mentioned earlier. Each grid cell can only have two high confidential bounding boxes with respect to one class, and it cannot go for multiple nearby objects. It cannot able to predict it. Then, even though it says that can be generalizable for a new aspect ratio and new scale bounding boxes, which is not available in the training data, but still it cannot go far beyond the outlier scales and aspect ratios. And also it works with the coarse features, but still downsampling can result into poor performance. And final thing is like when the small bounding box and big bounding box, small bounding box errors are not penalized very well in compared to the large bounding box errors. So these are the limitations. Hopefully some other paper like SSD and focal loss will be addressed in order to address these limitations of the YOLO. So finally, they are putting into a single convolutional neural network layer, avoiding the pre-processing layer in FASTA CNN, and they straight away, similar to fast RCN, straight away discretize the image directly rather than the pre-processing convolutional layer features, and regress and classify the objects in the image. And this is the figure one, and it's an upgraded version of fast RCN combined with multi-box, where it directly look into the image at once and try to regress and classify the objects in the image. Hopefully, you'll come up with the next video related to SSD in the next video. Thank you.